got a couple of things that I want to talk about. The first of which is your next exam. I would like to have your next test 1 week from today, so next Wednesday. That exam will cover S-domain circuit analysis as well as transfer functions and Bode plots. So effectively what we finish up today, maybe early on Friday, but I think we'll be able to finish everything today. That'll be what your test is about. Several of you all have asked me questions about the S-domain circuit analysis homework set. Particularly, you had a question about problems 1 and 3, where we had something going on before t is equal to 0 minus and how to account for that. So I'm going to help you guys that are still working on that sort that out here really quickly, because I thought I explained it sufficiently when we were going over that material, but I guess I was wrong. That's okay. So, if I'm remembering things correctly, this would be like homework set number 5, problem 1 was something like this, okay? You had a time domain circuit, Vs of t, so voltage source Vs of t connected to, let's say, a 6 ohm resistor. Here you had a 1 Henry source, and then over here you had a 1/2 farad capacitor. And your ultimate goal in this problem was to solve for Vx of t. Is this the right thing? Yeah. Okay. You were also told that you had a source voltage Vs of t that was given to be 20 U of negative t minus 20 e to the negative 5t U of t volts. Did I do that as a minus sign or a plus? Okay, I just can't read my thing. All right, that makes way more sense, actually. Okay, so just for what it's worth, I'm going to plot what this function looks like, because that's really going to tell us effectively what we're going to do. And this is something that I think that you guys might not have picked up on, okay? So if this is Vs of t as a function of time, so here's time on this axis. What does U of negative t mean? Let's start there. So that's a unit step function, but instead of extending out to the right infinitely, it extends out to the left infinitely. So effectively what we've got going on is a constant DC voltage of 20 volts until we hit t is equal to 0, at which point this guy turns off and this guy turns on. And so the right-hand portion of this is an exponentially decaying function whose initial value is 20. So we have a continuous voltage as a function of time. It's 20 volts DC until we hit t is equal to 0, and then it just exponentially decays. So effectively what we're going to do is we are going to analyze this circuit at t is equal to 0 minus, which is literally just DC circuit analysis, in order to get our initial conditions on our inductor current and our capacitor voltage. And then we're going to use those pieces of information to build our S-domain circuit model that is valid for t greater than or equal to 0 plus. Okay. So just for the sake of argument here, I'm just going to define this current IL of t like so, and I'm literally only going to pay attention to that at 0 minus, because I need those initial conditions to build my S-domain circuit for 0 plus. Okay. So at t is equal to 0 minus, this is a DC circuit. So we would have a 20 volt source like so. Here's a 6 ohm resistor. Here is my inductance through which my current IL at 0 minus flows. over here is my capacitor, across which we'll have our voltage Vx of 0 minus, which is the same thing as our capacitor voltage. So literally by Ohm's law, I can say that IL of 0 minus is 20 over 6 amps, and Vx of 0 minus is 0 volts. Anything particularly wild or crazy about that level of circuit analysis? For what it's worth, I hope to hell not, because you guys are juniors at this point. So anyway. So now we need to figure out what's going on for t greater than or equal to 0 plus. So for t greater than or equal to 0 plus, we're now going to convert this circuit into the S domain, but we only care about what's going on for 0 plus. So this bit right here no longer matters. Okay. So what is the Laplace transform of 20e to the minus 5t? I think it's just 20 over s plus 5, right? Our resistor is going to stay a resistor. Our inductor is going to have an impedance of S times L. Well, L was just 1 Henry. So we have an impedance of S here. And then I'm going to have a voltage source here. I'm choosing to do the impedance in series with a voltage source representation. I could have just as easily done impedance in series, or excuse me, in parallel with a current source, but this is the one that I like because it makes the circuit look less gross. Where this value, if I'm not mistaken, is, I wish I had written it down. Trying to think about how this is going to work, right? It's not just L times I, right?
10 over 3 times L.
Yeah, okay, okay. No, I guess it is just that, yeah. So it is literally just L times IL at 0 minus. So we could just write that as 20 over 6, 10 over 3, whatever you want to call it, okay? Since we don't have an initial condition on our capacitor, or a better way to put it, since the initial condition on our capacitor voltage is 0, we are not going to have to add a voltage source in series with that guy because it would just be a 0 volt source, which is a short circuit. Okay. So for this, we're going to have simply 1 over 0.5 S, which would be the same thing if we wanted to as an impedance of 2 over S. And then here is the Vx of S that we're looking for. And so we would simply analyze this circuit by whatever methodology seems appropriate. If I were doing this, I would probably do nodal analysis, just because my only unknown voltage, if I choose the bottom polarity, or excuse me, the bottom terminal as ground, is the Vx that I'm looking for. So this is circuit analysis. You guys know how to do that fine. So hopefully this unconfuses anybody who is still confused about what to do when we have a system with initial conditions. Simply analyze the circuit to find the initial conditions, plug them into our models for inductance and capacitance, and then do the analysis. All right, so any questions about this before we talk about Bode plot stuff? Great. Okay, so just as a reminder, I do need to leave early today to go to that champ module training stuff. So I hope to finish this today, but it'll be okay if we don't, because we've got time on Friday to do it as well. So in our last couple of lectures, we've been dealing with frequency response plots, both for a magnitude response and a phase response, when we had simple poles, simple zeros, and things like that. So effectively, all of our poles and zeros were real numbers. So now we're going to see what happens if we have a complex conjugate pole, okay? So let's say that I have a transfer function of the form h of s is equal to some arbitrary constant c, so that has nothing to do with capacitance, over s squared plus bs plus c. So I've got just a simple quadratic equation here in my denominator, right? We could put this in the form omega naught squared divided by s squared plus twice, and I'm going to pre-apologize, I am attempting to write the Greek letter lowercase zeta. It's going to look like a squiggle, okay? But that's what I'm trying to do, is the Greek letter lowercase zeta, okay? So twice zeta omega naught s plus omega naught squared, where omega naught is simply the square root of c, and this is the resonant frequency of the system, just like it was way back in circuits 2. And then zeta, that looks even shittier than normal, is equal to b divided by twice the square root of c. And this is what's known as the damping factor of our system, okay? So this concept of a damping factor is related to our Neper frequency that we saw in circuits 2, in some sense, okay? So this is telling us effectively different values for damping factor are what tells us whether our system is critically damped, over damped, or under damped, okay? So what we should expect is that when we have an overdamped case, effectively everything's going to work out pretty okay. When we have a critically damped case, things are also going to work out pretty much spot on. But when we have an underdamped case, we are going to have some sort of oscillation, right? So remembering what the response of an underdamped system is, we had an exponentially decaying sinusoid. So effectively, we're going to try to tie this information with what we've learned in circuits 2 and try to come up with something new, okay? So let's go through a few cases here, okay? Or actually, if we were to try to put this thing in our standard form, okay? So h of s in our standard form, and I'm talking about the standard form where we have our s terms over our pole frequencies and things like that in our denominator, right? We could write this as 1 over s over omega naught squared plus twice zeta times s over omega naught plus 1. So let me write this as standard form for Bode analysis. So literally, all I've done here is factor out omega naught squared from the numerator and omega naught squared from the denominator. Nothing, anything more difficult than that. Okay. And I'm putting it in this form because that's the form that we've been using for our Bodie plots and all of that kind of good stuff. So if zeta is greater than 1, then h of s may be factored to show that the system has two simple poles. So if we were to let zeta equal to 1.25, then for our system, we would have h of s is equal to 1 over s over omega naught quantity squared plus 2.5 s over omega naught plus 1. And this is the exact same thing as 1 over 1 plus s over twice omega naught times 1 plus s over half omega naught. Anytime zeta is greater than 1, it will be factorable like this. Yes. Star, that's a mistake up here. Thank you for that. Because I should have had s squared divided by omega naught squared and then factored out so that I'm squaring that thing. So thank you for pointing that out. You're 100% correct. I had made a mistake. All right. So in this particular case, we have simple poles and all of that kind of stuff to be dealing with. Nothing particularly wild or crazy. This is what's representing effectively the overdamped case, where our time domain response would simply be the sum of simple exponential functions. Okay. When, or if, zeta is exactly equal to 1, then h of s can be shown to have a repeated simple pole, right? So if we let zeta equal to 1, then h of s would simply be 1 over s over omega naught quantity squared plus twice s over omega naught plus 1, which is literally 1 plus s over omega naught quantity squared. This is critical then. We already know how to describe this. So now we're going to look at what happens when zeta is between 0 and 1. Can't be negative, so it's just going to be some number less than 1, okay? So when 0 is less than zeta is less than 1, h of s will have complex conjugate poles. So 4s is equal to j omega. And again, we're just kind of throwing away our sigma because we're only concerned with the frequency response, which is dependent on omega. Then our transfer function becomes something like this. So we would have h of j omega will be equal to 1 over j omega divided by omega naught, quantity squared, plus twice zeta j omega over omega naught plus 1. And we know that j squared is just -1, right? So effectively what we're going to have is 1 plus twice zeta actually j twice zeta omega over omega naught minus omega over omega naught squared. All right, let me just double check things here. So I took this j from inside here and I moved it to the outside so that I have a distinct imaginary part that I can recognize. I have a real part that consists of 1 minus the ratio of omega over omega naught quantity squared. Okay. So all of that seems fairly legit. So let's think about some things here really quickly. Okay. So for frequencies well below our resonant frequency, what's happening? So when omega is much smaller than omega naught, this term over here on the right-hand side effectively trends towards 0, right? It's not going to be particularly large. So we're going to have a number less than 1, and we're squaring it, which means it's going to be even smaller. Okay, we okay with that? Our imaginary part is also going to kind of trend towards 0 because we've got j2 times a number less than 1 times another number less than 1. So this guy in the middle is going to be rather small as well. So when we're well below our resonant frequency, then we could say that h of j omega will be approximately equal to 1. And thus, 20 log of the magnitude of h of j omega will be approximately 0 dB. Are we okay with that? So 4 omega is much greater than omega naught. What's going to happen? So this term over here on the right-hand side is going to be the dominant contribution, okay? So we're going to have some number significantly greater than 1, and we're squaring it. So this guy's going to be real big. This guy in the middle is going to be largish, but it's not going to be anywhere as large as this guy is going to be because we're squaring a large number, right? So this guy on the right-hand side will be much, much greater than 1, and it will be greater than the middle term. So as long as we're at a high enough frequency, this is actually just going to trend towards 1 over omega naught squared. We will actually have phase inversion as well, but because we're only dealing with the magnitudes, I'm just going to call this 1 over omega naught squared, okay? So h of j omega will be approximately -1 over omega naught squared, and thus 20 log h, the magnitude of h of j of omega. So this looks like effectively a repeated pole. So we're going to have a slope of -40 dB per decade, right? So we would have a single pole at omega naught and then a second pole at omega naught. So we'll see roll off of 40 dB per decade. So where this gets gross is when we're near our resonant frequency. Okay. So we've handled frequencies well below our resonant frequency. We have a nice 0 dB, so a flat response. We've handled things well above our resonant frequency. So we have just a constant -40 dB per decade decay. Okay. So effectively, thus far, everything looks like just a repeated pole. But when we get somewhere where this middle term is dominant, which is what happens when omega over omega naught, when omega is close to omega naught, we're going to see that things start to behave weirdly. And how our response looks in this area is going to be very, very dependent on the value of zeta. Okay, that's what I'm trying to get at. So let's write this out, okay? So for frequencies very close to omega naught, the middle term will become dominant. So 20 log of the magnitude of h of j omega will be approximately equal to the 20 times the log of 1 over twice zeta. So just to be really clear here, make sure we're all catching what I'm throwing. When we're very close to omega is equal to omega naught, I have 1 minus 1, or something very close to that, right? So only the middle term survives. The omega over omega naught looks like something very close to 1. So all I have left is this J2 zeta. When I'm looking at the magnitude, just throw the J away, because that's just telling me a phase shift, right? So we can make a table here really quickly, okay? So let's say that we put zeta in the left-hand column, and then 20 log of twice zeta in the right-hand column. So I want to be very clear about this. What's the relationship between 20 log of twice zeta and 20 log of 1 over twice zeta? A negative sign. That's literally it, right? Because this would be 20 log of 1, which is 0, minus 20 log of 2 zeta. So the only difference between what we've inferred here and what my table is going to look like is whether things should be above the graph or below the graph when we're taking into these effects into account, okay? So let's say that zeta is exactly equal to 1. I want you guys to throw 20 log of 2 into your calculator and tell me what you get. 6.02 dB. What if zeta is 1/2? Well, that's just 20 log of 1. We already know that that's simply 0 dB. What if zeta were 1/4? What's 20 log of 1/2? Negative 6.02 decibels. What if zeta were 0.1? So 20 times the log of 0.2, I get negative 13.979. For 0.05, I got negative 20 dB. And for 0.01, I got negative 33.979 dB. Okay. So what I'm going to do here is I'm going to draw a graph of what our frequency response might look like as we have different values of zeta. Okay. So let me just pick some colors here. So I'm going to do this guy in green. We'll do the next one in red, and then purple, and then hot pink, and then orange, and then blue. I haven't used that one yet. So here is 20 log of the magnitude of h of j omega, like so. Here's omega. So let's put omega naught here in the center, and then this will be 0.1 omega naught. This will be 0.01 omega naught, 10 omega naught, and 100 omega naught. So let me make this negative 20 dB, minus 40 dB, and so on and so forth. Okay. So let's start with the red one, actually, because that's the easiest one to do. Okay. So effectively, what this value right here on our table is telling us is how much we need to shift our graph in the area of our resonant frequency. So with a zeta value of 0.5, we don't shift it literally at all. Okay. So we would have something as simple as it's at 0 dB until omega naught, and then that it's decaying at a slope of negative 40 dB per decade, which would look like this. Easy enough, right? Now let's do zeta is equal to 1. So what we should see is effectively just a nice, smooth frequency response plot where when we're at the region of omega naught, we're actually 6 dB below that 0 dB threshold because of this number right here. Shit, goodness gracious. So something like this. Okay. So before we go on from here, let's just contextualize things, okay? When we were drawing our smooth line plots for a simple pole, this distance between our straight line approximation and our smooth curve was 3 dB. Now we're seeing a difference of 6 dB because we're doubling the difference. So this exactly agrees with what we've been doing before. It is literally nothing new at all. It's just exactly what would happen for a repeated pole. Okay. Now here's where things get a little bit interesting. Okay, so let's do the purple one next. So we are going to have an increase of 6 dB in the region of our resonant frequency. So what we're going to have is something like this. It's going to start off at 0, and then when we get close to our resonant frequency, it's going to jump up like so. Then it's going to come back down, and it will catch up to that negative 40 dB per decade slope that we had earlier. And effectively, all of these other guys are going to look something similar to that, except that it's going to get steeper and steeper and steeper in this region. Okay. So for our pink one, we're at 13 dB, so they're around here. So something like this. For our orange one, we would be at negative 20 dB, or positive 20 dB, since we're doing 1 over twice zeta. I don't know why I wrote the table like that in my notes. It would have made more sense to just do it. But anyway, I'll fix that for next year maybe. And lastly, here we would have 33, which would be somewhere in the ballpark of there. So that's what our frequency response curve would look like. We're going to have a peak value that is 33.979 dB above the 0 dB level. So it's going to shoot up to there and then fall back down. And as we get larger than omega naught, it needs to catch back up to that negative 40 dB per decade slope. Toby, what's up?
So, kind of,
Sure.
so this is drawn this way because the data is around.
Let me do something slightly different.
So why does it catch back up with a negative 40?
Because we know that for omega greater than omega naught, this starts looking like just 1 over omega naught squared, which would be nothing more than a simple pole, a simple repeated pole. So it should have a slope of negative 40 dB per decade. Because a single simple pole has a slope of negative 20 dB per decade.
So as the omega naught, it hits that constant and then jumps back down to that.
Yeah, exactly right. So this seems kind of weird, but this is actually incredibly useful. We very regularly, as electrical engineers, design circuits to have responses like this in communication networks. Because let's think about what this thing means in context, okay? So when we are below this area, we are neither attenuating nor amplifying our signal at all, right? But when we get into the region very, very close to our resonant frequency, all of a sudden we have amplification. And this is passive amplification. We can do this with just resistors, capacitors, and inductors. We don't need an op amp for that to happen. And then once we get beyond this frequency, we fall off. So this is a bandpass filter. Okay. It's a bandpass filter that significantly boosts our frequency of interest. And the steeper that we make this thing, the more selective our frequency actually is. Okay. So filters like this are how our cell phones work. This is how we only hear our conversation and not everyone else's conversation, because our cell phone network is at a frequency of 1.9 megahertz or something like that. I can't remember right off the top of my head, but I believe that's what at least 3G US telephony was, 1.9 megahertz. So we cram literally tens of thousands of different phone calls into this very, very narrow frequency band. And so we need to be able to design filters that are highly selective so that we only hear what we're supposed to hear and we don't hear everybody's stuff. Okay. So our next big topic is what we're going to start covering on Friday, and that will be resonant circuits. So we are going to explore circuits specifically whose frequency response is going to look something like this, and then talk about how we can design them for specific applications. All right. So that's enough out of me for today. And wouldn't you know it, I finished up exactly when I wanted to for the first time ever. I'll be damned.